Hi everyone, this is Dr. G. Ravindranath Reddy working as Assistant Professor of Mathematics in MLR Institute of Technology, Hyderabad. So we are discussing the numerical methods and integral transform course. In that, now we are discussing applications of Laplace transform. So in this video, we are discussing how to solve the differential equations by using Laplace transform technique. So this is one of the application we are going to discuss of Laplace transform. So the Laplace transform, we know that already we have discussed about the Laplace transform and inverse Laplace transform in the previous videos. Now here we are going to discuss the applications of Laplace transform. So this Laplace transform is a powerful tool for solving the differential equations, especially those with constant coefficients. So here, by using this Laplace transform, you are going to find out the solution for the linear differential equations. Whereas by using analytical methods, we have seen without finding the complementary function and particular integral, we are going to find out the directly particular integral, say particular solution for the given differential equations by using this Laplace transform. So here there is no concept of complementary function, there is no concept of particular integral here. So without finding these two, we are going to find out the particular solution for the given differential equation. Okay, so now, for example, if you take the differential equation now, by using this by using this Laplace transform, if you want to find out the solution for the given differential equation, along with the differential equation, we have to get some initial conditions here. Suppose if you take the second order differential equation, then you will get two initial conditions. Suppose if you have a differential equation of order 3, then along with that differential equation, you have to get three initial conditions: y of 0, y dash of 0 and y double dash of 0. Without using these initial conditions, then it is not possible to find out this solution by using this Laplace transform technique. So once again I will repeat. So in order to find out the solution for the given differential equation by using this Laplace transform, along with the differential equation, we have to know some initial conditions. By using these initial conditions, we are going to find out the solution for the given differential equation using Laplace transform technique. So first we will discuss the procedure. We will discuss the procedure and then we will take some examples how to solve the differential equations by using Laplace transform. So let us consider this procedure. So first, we have to convert the given differential equation in the form of y dash, y double dash and y triple dash and so on. So sometimes they will give the differential equations as d square y by dx square minus 2 into dy by dx plus 3y is equal to some function in terms of 0 or equal to 0. So whenever we are having this type of differential equations, then we have to convert this differential equation in the form of y dash, y double dash and y triple dash. So this d square y by dx square can be written as y double dash minus 2 into dy by dx, we can take it as y dash plus 3 into y is equal to 0. So we have to convert the given differential equation in this standard form. Okay, that is the first point we have to remember. Now once after converting the given differential equation in terms of y dash, y double dash and y triple dash, then we have to take the Laplace transform on both sides. Now imagine that this is our differential equation. So we have converted the differential equation in the form of y dash, y double dash and so on. So now after converting into this form, then in the second step what we have to do is we have to apply the Laplace transform on both sides. That is Laplace transform of y double dash minus 2 into y dash plus 3 into y is equal to Laplace transform of 0. Okay, so now apply the linearity property, then you will get Laplace transform of y double dash minus 2 into Laplace transform of y dash plus 3 into Laplace transform of y, and Laplace transform of 0 is 0. So like this, in the second step, these are the 2 points we have to remember. Apply the Laplace transform on both sides, then apply the linearity property of Laplace transform, and then apply the Laplace transform for each term in the given differential equation on both sides. So now in the third step, what we have to do is, so here we are having Laplace transform of y double dash, Laplace transform of y dash. Now we have to use this standard formulas here. Suppose whenever we are having Laplace transform of y dash, that is Laplace transform of derivative formulas we are using now. So this Laplace transform of y dash of y. So wherever we are having Laplace transform of y dash, we can replace that value with s into y bar of s minus y of 0. And suppose if we are Laplace transform of y double dash of t, then we can replace that value with this, and Laplace transform of triple dash, y triple dash is equal to with this. So now, for example, if you observe this first term, Laplace transform of y double dash, so we can take this, we can replace this value with this second formula, that is s square into y bar of s minus s into y of 0 minus y dash of 0. So we can replace this Laplace transform of y double dash with this, and similarly you also replace this Laplace transform of y dash by using this formula. So once by applying these formulas, then this y double dash, Laplace transform of y double dash, Laplace transform of y dash, all will be converted in terms of y bar of s, y of 0 and y dash of 0. Now here, after the completion of this third step, so in this we can see some initial values, that is y of 0, y dash of 0 and y double dash of 0. So you can find this one. So now what we have to do is, we have to replace y of 0, y dash of 0, y double dash of 0, all these values with the given initial conditions. So y of 0, that will be given in the problem. Y dash of 0, this value is also given in the problem. Y double dash of 0, this value is also given in the problem. So we have to replace these values with the initial conditions which are given in the problem. So that is our fourth step. Now what we have to do is, after replacing y of 0, y dash of 0 and y double dash of 0s with these values, then we have to do some simplifications, and after doing that simplifications, we have to get y bar of s. We have to get that y bar of s in terms of s. So you take y bar of s terms one side, and you send the remaining terms to other side, and then take the y bar of s common from the remaining terms which are in the LHS side, and then you send that coefficient of y bar of s to the other side, it becomes in the denominator. So we have to do these simplifications in the fifth step. So now then it will be converted to y bar of s is equal to, then you will get a function in terms of s. Then finally we have to apply, suppose if there is a scope to split that given function, this function which is in the RHS side, if it is possible to split into a partial fractions, we can split into a partial fractions, and then finally you apply the inverse Laplace transform on both sides. So once after applying the inverse Laplace transform on both sides, then you complete that inverse Laplace transform, then automatically you will get that y value as a function of t, which is our required solution for the given equations. So this is the procedure. So first we have to convert the given differential equation into this standard form, then take the Laplace transform on both sides, then use these formulas and convert that Laplace transform of y dash, Laplace transform of y double dash, Laplace transform of y triple dash, and so on into these formulas in terms of y bar of s, y of 0, y dash of 0 and y double dash of 0. Then replace the initial values y of 0, y dash of 0, y double dash of 0 with their initial conditions which are given in the problem. Then simplify and try to get that y bar of s value in terms of s. Then apply inverse Laplace transform on both sides, then find out that inverse Laplace transform of the function f bar of s, then automatically we can get our required y value in terms of t, which is our required solution for the given differential equation using the given initial conditions, which satisfies the given initial conditions. So this is the procedure we have to follow to solve the given differential equations using Laplace transform technique. Now let us take one example here. We'll follow this procedure step by step and we'll see how to get that solution for the given differential equation. So this is our problem. Solve y triple dash plus 2y double dash minus y dash minus 2y is equal to 0. This is the given differential equation he has given. Now our task is, by using this Laplace transform technique, for this given differential equation we have to find out the solution. So finding the solution is nothing but getting the value of y in terms of t. There is this relation we can consider the solution for the given differential equation. So since we are applying the Laplace transform technique, so in order to get the solution by using this Laplace transform technique along with the given differential equation, we want some initial conditions here. So how many conditions we want here? Because this is the differential equation of order 3, y triple dash, this is the highest derivative, y triple dash is the third order derivative for the given y. So here the order, the number of conditions must be equal to the order of the given condition. So order is 3, so we have to get 3 conditions here. One is y of 0, y dash of 0 and y double dash of 0. So since the order of the given differential equation is 3, we have to get 3 initial conditions here. Now by using these initial conditions for this differential equation using this Laplace transform, we have to get the solution. That is the meaning of this problem here. So let us take the given differential equation first. Given that this is the given differential equation, y triple dash plus 2y double dash minus y dash minus 2y is equal to 0. That is the first step here. Whatever the differential equation he has given, the differential equation is in terms of y dash, y double dash and y triple dash. So no need to convert into this one. You directly, we are having the given differential equation in our standard form. Next step what we have to do is we have to apply the Laplace transform. Take the Laplace transform on both sides for this given differential equation. We get, so Laplace transform of first term plus 2 into Laplace transform of second term minus Laplace transform of third term minus 2 into Laplace transform of that last term is equal to 0. Why we are taking 0 here? Laplace transform of 0 is always 0. So after taking this Laplace transform on both sides, we will get, now what we have to do is, for this we have Laplace transform of y triple dash. Laplace transform of y triple dash, we have to use the standard formulas. Laplace transform of derivative formulas, use the derivative formulas here. Whatever we have taken that formulas in the working procedure, you take that help of that formulas, and you now you expand this Laplace transform of y triple dash of t, Laplace transform of y double dash, Laplace transform of y dash and Laplace transform of y. That is our simple. So now use that formulas here. Laplace transform of y triple dash. So triple dash third derivative means we have to take s cube into L into Laplace transform of y of t minus s square into y of 0 minus s into y dash of 0 minus y double dash of 0. This is our formula. Laplace transform of y triple dash is equal to y cube, y bar of s, or we can take it as a Laplace transform of y of t, both are same, minus s square into y of 0 minus s into y dash of 0 minus y double dash of 0. That is the formula we are having. I have used this formula. And similarly the second term is y Laplace transform of y double dash. So Laplace transform of y double dash is equal to s square into y bar of s, or we can take it as s square into Laplace transform of y of t, both are same, minus s into y of 0 minus y dash of 0. So use this formula for the second term, and similarly go for this Laplace transform of y dash. So s into Laplace transform of y of t minus y of 0. So you keep that Laplace transform of y of t as it is, the last term is equal to 0. So now we have applied that formulas. Third step is completed. Now once if we observe this step in this step here, we can find y of 0, y dash of 0, y double dash of 0. And here also we are having y of 0, y dash of 0, y of 0. So now what we have to do is we have to replace y of 0. So here in the problem itself he has given y of 0 equal to 0. So given that y of 0 is equal to 0 and y dash of 0 is also equal to 0, and finally he has given y double dash of 0 is equal to 6. Now in this, wherever we are having y of 0, replace that with 0. Wherever we are having y dash of 0, replace with 0. And y double dash of 0, replace with 6. So in the next step, what we have to do is, we have to replace these initial conditions here. So after replacing here, we get, so here this term becomes 0, y of 0 is 0, we can neglect this. Y dash of 0 is also equal to 0, so this also we can neglect this. These terms we can neglect, and here also this term will be neglected and this term is neglected here because y dash of 0 is 0, and here also we can neglect this y of 0. Y of 0 is 0. So after neglecting here, we get in the first term we will get s cube Laplace transform of y of t. So here we have taken s cube into Laplace transform of y of t minus, here we are having y double dash of 0. Here we know that y double dash of 0 is equal to 6. So y double dash of 0 equal to 6. So here 2s square into Laplace transform of this. So this is our, after replacing that initial conditions, this is our resultant equation we get. So from all these equations, from all these terms, I want to take Laplace transform of y of t, Laplace transform of y of t common from these four terms. So after taking from the first term, if we take Laplace transform of y of t common, the remaining one is y cube. Here we are having 2s square, keep 2s square, here minus s, here minus 2. So this is Laplace transform of y of t, and the remaining term is minus 6. So you send this minus 6 to this side, it becomes 6. Okay, so now finally we got this value. Now you keep this Laplace transform of y of t as it is and send this coefficient to this side. So it becomes Laplace transform of y of t is equal to 6 by s cube plus 2s square minus s minus 2. Okay, now what we have to do is, since it is a cubic polynomial, so try to convert that cubic polynomial in terms of linear factors. So for this, you will get a linear factors as s minus 1 into s plus 1 into s plus 2. Now you consider this as equation 1 here. So now what I am doing is, I want to split this one into a partial fractions, because in the denominator we are having a product of 3 linear factors. So first I will split this one into a partial fractions here. So then I will find out the value of y of t later. So for this I will consider this 6 by s minus 1, s minus s plus 2, s plus 1. So since all these are in the previous videos we have seen how to split this function f bar of s into a partial fractions and how to get that inverse Laplace transform. In the previous videos we have seen. So now since these 3 factors are a linear factors, so we can take a by s minus 1, b by s plus 1 plus c by s plus 2. Now our task is, we have to get the value of a, we have to get the value of b, and we have to get the value of c. So now we have a shortcut methods how to get this a value, b value, c value, which we have discussed in the previous video. So once again I will repeat that same process here. So now suppose if you want to get this a value first, so now whatever the denominator we are having under this a, equate that denominator to 0. So that is, denominator is s minus 1 equate that value to 0, you will get s is equal to 1. Now I am finding the value of a. So now go to the LHS part. So whatever the factor we are having under the denominator a, here in the LHS side you neglect this factor, and in the remaining function after neglecting s minus 1 you substitute s is equal to 1 here. So if you substitute s is equal to 1 here, you will get 6 by, so replace s1. So 1 plus 1 which is equal to 2, 1 plus 2 which is equal to 3. So you will get this value is equal to 1. So you will get a is equal to 1. Now we got that. Now our task is finding the value of b. So what is the denominator under b here? S plus 1. Equate that value to 0. You get s is equal to minus 1. And in the same procedure, follow the same procedure. So whatever the factor we are having as the denominator of b, you go to this LHS part and neglect that factor, and in the remaining you replace s is equal to minus 1. You will get, so 6 by minus 1 you will get minus 2. So minus 1 plus 2 you will get 1. So which is 6 by minus 2 which is equal to minus 3. So this is our b value here. And similarly follow the same procedure for c and get the value of c here. So you will get, after finding this, a is equal to, we got a is equal to 1, b is equal to minus 3 and c is equal to 2. We replace these values here, we got this simple function. So this is possible only by resolving into a partial fractions here. Now in equation 1 I want to replace this value with this function. So you will get Laplace from equation 1, we will get Laplace transform of y of t is equal to, so in place of this function I want to replace this function here. So 1 by s minus 1 minus 3 by s plus 1 plus 2 by s plus 2. Now apply L inverse. We want only y of t value, we don't want this Laplace transform here. So send this Laplace transform to this side or apply inverse Laplace transform on both sides. You will get L inverse of 1 by s minus 1 minus 3 into L inverse of 1 by s plus 1 plus 2 into L inverse of 1 by s plus 2. All these are, we have seen these formulas which are of the form 1 by s minus a, which is given by e power at. L inverse of 1 by s plus a, this value is given by e power minus at. Now use these formulas, we will get our required solution here. So L inverse of 1 by s minus 1, this is the formula. In place of a, substitute 1, you will get e power t, this is our function, minus 3 into s plus a. So replace a with 1, you will get e power minus t. So replace a with 2, you will get e power minus 2t. So this is our required solution for the given differential equation here. So once if you observe this one, the procedure what we have seen. So while you are discussing this solving the differential equations using analytical methods, so there if you want to find out the solution, here we have to find out the complementary function and particular integral here. That is our procedure by using analytical methods. But here there is no concept of complementary function, there is no concept of particular integral here. So directly, without finding this complementary function and particular integral, we can directly get the particular solution for the given differential equation in terms of t. So this is the useful technique we are having. So very important application under this Laplace transform here. So let us take one more example that we will discuss. So now we will take the second order differential equation d square y by dt square plus 2 into dy by dt minus 3y is equal to sin t. This is the second order differential equation. Since the order of this differential equation is 2, the initial conditions must be equal to 2. That is y is equal to dy by dt is equal to 0 when t is equal to 0. So this y is equal to dy by dt equal to 0 when t is equal to 0. This entire condition is similar to y of t. In place of t here we will take 0. Y of 0 is equal to dy by dt. We can take it as y dash. Since t is equal to 0, y dash of 0. So this value is equal to 0. So these conditions also we can write in this standard form. Y of 0 is equal to y dash of 0, which is equal to this value. So sometimes in this way also they will give the initial conditions. We have to convert that conditions into our standard form. Y of 0, y dash of 0, y double dash of 0. Okay, now we'll see how to solve this second order differential equation by taking the help of these initial conditions here. Follow the same procedure. Procedure is same, but differential equation is different here with the initial conditions. So now take the differential equation. Now while you are discussing the procedure, we have to convert the given differential equation in the form of y dash, y double dash and y triple dash and so on. So here we don't have the differential equation in this standard form. So our task is we have to convert into standard form. So that is d square y by dt square. I will write this value as y double dash plus 2 into dy by dt. I will take this as a first derivative. So I will replace that with y dash minus 3 into y is equal to sin t. So this is our given differential equation in terms of y dash, y double dash and y. Now immediately you apply the Laplace transform on both sides. So apply the Laplace transform. So Laplace transform of y double dash of t. So y double dash or y double dash of t, both are same, no need to worry about this. By default, suppose if you have taken y double dash, by default this is y double dash of t. So Laplace transform of y dash of t minus 3 into Laplace transform of y of t is equal to Laplace transform of sin t. So we have applied the Laplace transform on both sides. Now here use the standard formulas, Laplace transform of y double dash, Laplace transform of y dash formulas here. So you will get s square into Laplace transform of y of t minus s into y of 0 minus y dash of 0. This is the formula for this Laplace transform of y double dash plus 2 into Laplace transform of y dash, 2 into Laplace transform of y of t minus y of 0 minus 3 into Laplace transform of y of t is equal to Laplace transform of sin t. We have the formula Laplace transform of sin at is equal to a by s square plus a square. Here a is 1, so 1 by s square plus 1. So this is the Laplace transform of sin t. Now we have applied the formulas. Now once after applying that formulas, once if we observe, we can find y of 0, y dash of 0 and y of 0. And we know that y of 0 and y dash of 0, he has given that values are equal to zeros. So if you replace y of 0 with 0, this term we don't get this term. Y dash of 0 also becomes 0, this particular term. And this terms in the second term, the second y of 0 is also becomes 0. So finally you will get s square Laplace transform of y of t plus 2 into s into Laplace transform of y of t minus 3 into Laplace transform of y of t. Only these terms will remain after substituting that initial conditions here. So now take the common of Laplace transform of y of t. So here we are having Laplace transform of y of t. If you take outside, this coefficient is s square. Here also we are having a Laplace transform of y of t. The coefficient is 2s. Keep this 2s. Here we are having Laplace transform of y of t, coefficient is minus 3. From these three terms, I have taken the Laplace transform of y of t common and send this coefficient to this side. You will get Laplace transform of y of t is equal to 1 by s square plus 1 into s square plus 2s minus 3. So this coefficient, it becomes in the denominator here. Now you consider this as equation 1. So now if you want, you can send this L to this side. It becomes y of t is equal to L inverse of this. Now our task is we have to find out the inverse Laplace transform for this. So now whenever we want to find out the inverse Laplace transform, we can take the help of partial fractions. If it is possible to split this function into a partial fractions, we can go for that partial fractions here. So now consider, so separately I will consider this function and I will split into a partial fractions here. So s minus 1 is a linear factor, so a by s minus 1. The second factor s plus 3 is also a linear factor, so we can take plus b by s plus 3. And s square plus 1, this is a quadratic factor which is not reducible into a linear factors. So s square plus 1, it is not possible to split like this. So whenever we are having irreducible quadratic factor, then for that we have to consider AB is completed. Now go for the next alphabet, CS plus D by that irreducible factor s square plus 1. Now our task is A value, B value, C value and D value here. Okay, so since for these two A and B, we can find out the values of A and B very easily by using the shortcut method which you have studied in the previous slide. So put s is equal to 1. By neglecting this factor, you will get our A value, and put s is equal to minus 3 in order to get the B value here. By neglecting this B value in this, you can get our values here. So now if you want, we can follow that procedure. Otherwise we can follow the standard procedure by taking the LCM here. So what is our LCM here? So LCM is s minus 1 into s plus 3 into s square plus 1 of A of s plus 3 into s square plus 1 plus B into s minus 1 into s plus 3 plus CS plus D into the two linear factors s plus 3. So this denominator and this denominator gets cancelled, only the numerator will be equal. So this is our numerator what we have taken here, and this is equal to 1. Okay, now what we have to do is we have to equate. So put s is equal to 1, you will get A value. Put s is equal to minus 3, here you will get our B value here what we discussed. Now our task is we have to find out C value and D value here. So how can you find out that C value and D value here? By equating s cube coefficients, or by equating s square coefficient, or by equating s coefficient, or by equating constant coefficients. So like this, we can apply any one of these four options which is suitable to get the value of C and D. Okay, so now by equating s cube coefficient on both sides, now what we have to do is you remove these brackets here by multiplying with here you remove these brackets. So suppose if you remove this, you will get s plus 3 into s square plus 1. First you multiply this s with these two terms, s into s square, you will get s cube, plus s into 1, you will get s, plus now go for this 3s square plus 3, and similarly you multiply the coefficient of B. So s into s square, you will get s cube, plus s into 1, you will get s, multiply minus 1 into s square, you will get minus s square, minus 1 plus 1, you will get minus 1. So like this you multiply this, you will get in the first term s cube coefficient is A, in the second term s cube coefficient is B, in the third term also you will get our s cube coefficient as C. So like this you will get A plus B plus C is equal to, so here in this RHS side we don't have s cube coefficient, so that s cube coefficient can be written as 0 into s cube. The coefficient of s cube is 0. Suppose any term is missing, either a s cube term is missing here, we can consider that coefficient of s cube is 0. So now coefficient of s cube is equal to 0. So now you send this, we know the value of A and B, so replace that C is equal to minus A minus B, replace that A value, B value here, and simplify, you will get c is equal to minus 1 by 10. Now our last one is we getting the value of d. So now in order to get the value of d, I want to similarly here also I want to compare with the s square coefficients on both sides. So s square coefficient, these are the coefficients we will get, and we don't have that s square coefficient in the RHS side. We are having only a constant term, that is 1. So in this we don't have s square coefficient, we don't have s square term, so we can take that coefficient of s square as 0. Now from this equation find out the value of d. You will get that d is equal to minus 1 by s. Now in that previous slide, wherever we have a, b, c and d, we can replace that a, b, c and d values with these values here. So you will get from equation 1, you will get Laplace transform of y of t is equal to, so a in place of a we got the value that is equal to 1 by 8, replace, and b we got that b is equal to minus 1 by 40, and c just now we got c is equal to minus 1 by 10 into s, d we got minus 1 by s. So now you send this L to this side, it becomes L inverse here. So L inverse of y of t is equal to L inverse of this. Separately apply the linearity property, that is L inverse of first term, L inverse of second term, L inverse of third term, and L inverse of fourth term. So okay, apply the linearity property. So now already this is of the form L inverse of 1 by s minus a. So we can take this value is equal to e power 80. So take that value 1 by 8 into e power a means 1, so e power t. And similarly this is also the same formula, L inverse of 1 by s plus a. So we can take this value is equal to e power minus 80. So here a is equal to 3, so we can take e power minus 3t minus 1 by 10 into, so we have the standard formula L inverse of s by s square plus a square. So this can be written as cos 80. So here in place of a, here we are having 1, so this can be written as L inverse of s by s square plus 1. This can be written as cos t, since in place of a, here we are having 1. So you take this value as, and similarly we are having another formula L inverse of 1 by s square plus a square. So this can be written as sin 80. So a is equal to 1, so it becomes sin t. So this is very simple. After converting into a partial fractions, that complex function, we are converting that complex function into a simpler function by using the concept of partial fractions, and then we are using these standard formulas of inverse Laplace transform. So once if you get this all inverse Laplace transform, all the terms, then we can get our required solution for the given differential equation here. So in this video we have seen the applications of Laplace transform. So in that applications of Laplace transform, we have seen how to solve the given differential equation by using Laplace transform technique. Now in the next video we will go for the next concept, that is Fourier transforms, in the next video. Thank you.